So this video is going to take you through the next part of this topic, organic chemistry. We're going to be looking at alkenes and their chemistry, and so that's starting from point 2.5.12 on the specification, and we're going to be starting on page 23. So as I've said, we're going to look at alkenes in this video, and alkenes is our next family of organic molecules. We have looked at alkanes, and they were a separate family of organic molecules. They were a separate homologous series. And what I want to do just before we look at them is to remind you of that definition of a homologous series, which is essentially another word for a family of organic molecules. So a homologous series is a family of organic molecules that have the same general formula, show similar chemical properties, show a gradation in their physical properties, and differ by a CH2 group. And we saw that alkenes fitted every single part of this definition, and we're going to see that alkenes do as well. But they are a completely different family of molecules. We said we were going to look at 4 homologous series. We're going to look at alkanes, alkenes, alcohols, and carboxylic acid. So alkenes take us on to our second family of organic molecules, our second homologous series. And what you need to make sure is that you don't mix them up with alkenes. You can see that these are alkenes. The spelling of them only differs by one letter, this central letter. Alkenes has an A and alkenes has an E, but actually we'll see they're completely different molecules and show completely different chemical reactions. And so you must notice the difference there. These are alkenes. So alkenes are structurally different to alkenes in that they are unsaturated hydrocarbons. So where we saw alkanes were saturated, alkenes are unsaturated, and I'll explain what that means in a second. They are unsaturated hydrocarbons. And what did we say that word hydrocarbons meant? Well, it means they contain hydrogen and carbon only. So the hydro part means hydrogen, the carbon part means carbon, but they must not contain anything else. So they're molecules that contain hydrogen and carbon only, but they are unsaturated. So what do we mean by this word unsaturated? We'll see it slightly more when we see the structure of these alkenes, but essentially alkenes have a functional group of a C double bond C. So there must be at least one double bond within the carbon chain of an alkene. There must be at least one carbon-carbon double bond. And that means they can't be saturated with hydrogen atoms. So if we look, for example, at ethene, so eth means that there's going to be 2 carbons. And so if I draw that, if there's only 2 carbons, the double bond must be between these 2 carbons. If we think again about how many bonds carbon can have, can you remember? Carbon must have 4 bonds. So that means each of these carbons can only have 2 more hydrogens. They can only have 2 more hydrogens. So each of those carbons is not saturated with hydrogen atoms because actually 2 of the bonds are used up by bonding to another carbon. So this is ethene. And let's recap on what ethane was. So ethane is our alkene. Ethene was our alkene. So ethane was again 2 carbons, but this time it just has a single bond between the 2 carbon atoms because it's an alkene. So let's think about how many hydrogens it needs. Well, each of these carbons is going to need 3 hydrogens attached to it. So we can see this is saturated. We refer to this as being saturated because the carbon atoms are completely saturated with hydrogen atoms, whereas alkenes are unsaturated because you can see for the carbons in this molecule, they're only bonded to 2 hydrogen atoms rather than the 3 in ethane. And that's because they have this carbon-carbon double bond, which is taking up 2 bonds for each carbon rather than just 1. So that's what that word unsaturated means. We also see how alkenes are different than alkanes in that they possess what we call a functional group. And a functional group is essentially a group of atoms that where a reaction happens within a particular molecule. So what we find with molecules is that reactions happen at a particular atom within the molecule or a group of atoms. Alkanes didn't have a functional group, and we saw as a result that they're very unreactive. And they're very unreactive because they don't have a functional group, and we saw their only reaction was combustion. Whereas alkenes do have a functional group. Their functional group is this carbon-carbon double bond. So if you write in your notes the functional group is a C, then double bond represented by 2 dashes and then another carbon atom. So let me highlight that within ething. So here's the functional group here. And what we see if we study the reactions of these molecules further is that that's where the chemistry happens. That's where the reactions happen with these molecules. With ethane, there is no functional group, and that's why it is unreactive. So we'll see that alkenes are much more reactive than alkanes. So there will be a couple more reactions for you to learn for these molecules. So the presence of this functional group makes alkenes more reactive than alkanes. As we know from our definition of our homologous series, they all follow the same general formula. The general formula of an alkene we can actually see from our molecule ethene here. So if we look at ethene again, how many carbons are there? There are 2 carbons. How many hydrogens are there? There are 4. So remember, N represents our number of carbons. So N here is 2. And then we can see that H is 4. 4 is a multiple of 2. If we multiply N by 2 in this case, we get 4. So our formula for alkenes is actually CnH2n. Remember how for alkanes it was CnH2n plus 2, but here we've lost the plus 2. Why do you think we've done that? So I've written that off to this side here. You don't necessarily have to write this in, but you can see we have essentially lost this plus 2 of our general formula of alkanes. And that's because, again, these alkenes are unsaturated. Because of the double bond, there's not as much room for hydrogens. And so as a result, we lose a total of 2 hydrogens per molecule, essentially. So an alkene will have 2 less hydrogens than the corresponding alkane. So if you look at ethene versus ethane, again, ethene, its formula is C2H4, whereas ethane, we can see here there's 2 carbons, 6 hydrogens, so its formula has 2 more hydrogens in it. Okay, so alkenes will have 2 less hydrogens than the corresponding alkane. So it's up to you. Some people find it helpful to learn this general formula. You are sometimes asked as a 1-mark question, what is the general formula of alkenes? What is the general formula of alkenes? So it's worth learning. But sometimes you can just get the formula from drawing it out. But what we can use this general formula to do is to get the specific formula of any length of an alkene. So if you were asked what's the formula of an alkene that contains 20 carbons, well, you wouldn't really want to draw out an alkene that represents or that has 20 carbons in it. It would be much quicker to just use the general formula. So let's remember that alkenes have a general formula of CnH2n. Okay, and what we're being asked to do here is to find the formula of an alkene containing 4 carbon atoms. So if it contains 4 carbon atoms, then N is going to equal 4. So if N is equal to 4, that gives us the number of carbon atoms, but we need to work out how many hydrogen atoms we have, and we can see that is given by 2N. So there's twice as many hydrogens as there are carbons within alkenes. So 2N is 2 multiplied by 4, which is 8. So that means that I have 4 carbons, 8 hydrogens, and so my formula is simply C4H8. So with alkenes, it's easy. Essentially, it's just double the number of hydrogens as you have carbons. You could do that literally for any length of alkene. If I told you you had 30 carbon atoms, it would just be simply C30H60, because there are twice as many hydrogens as there are carbons. So we're going to look now at the name, molecular formula, structural formula, colour and state of some specific alkenes. And what you should remember from earlier on in this topic is that organic molecules are always named by the length of their chain and the family of organic molecules that they belong to. So we know the start of the name is determined by the length of the carbon chain. And we have looked at this with alkenes, and alkenes are named exactly the same way. So the first 4 you need to learn. After that it kind of makes sense depending on the name. So for example, meth, how many carbons is that? 1. If there's 2 carbons in the chain, what's the start of the name? F. If there's 3 carbons in the chain, that's prop. And if there are 4 carbons in the chain, that is but. After that it makes sense, so pent is 5, hex is 6, and so on. Then the ending of the name, it is determined by the family of organic molecules that we're working with, and in this case, alkenes end in ENE. So for example, if we had an alkene with 3 carbons, the start of the name would be prop, and the end of the name would be ene. So we would have propane. So we're going to see that in the table below, and we're actually going to draw some of these molecules as well. Okay, let's start filling this table in. What you might notice is that the first one we're going to look at has 2 carbons in it. You might ask, why is there not an alkene that has just 1 carbon in it? In other words, why do we not have methane? Well, if you think about it, to make a molecule an alkene, it must contain the carbon-carbon double bond functional group. It must contain a carbon-carbon double bond. In other words, I must have at least 2 carbons. Otherwise, I'm not going to be able to have that carbon-carbon double bond. So actually, there is no such thing as methane, because methane means that there's just 1 carbon, and we can't have that in an alkene. So actually the first alkene in our series is ething, because it has to have at least 2 carbons. So because there are 2 carbons in the chain, the start of the name is ETH, and because it's an alkene, the end of the name is ENE. So this molecule is called ething. For the molecular formula, let's think of the general formula. The general formula of an alkene we've just looked at is CnH2n. So we can very easily work out what the molecular formula of ethene is, because we know that N is equal to 2. There's 2 carbons. So that's C2. And then we can see from our general formula that there are twice as many hydrogens. For hydrogens, I simply do 2 times by N. 2 times by 2 is 4. So ethene is going to have a molecular formula of C2H4. Structural formula now. These molecules are going to look slightly different than our alkanes, and that's simply because of the double bond. And if we were in class, we would get our molecule kits out at this point and be able to build these molecules and see the shape for ourselves. But unfortunately we can't do that. But let me show you by drawing this, and this is what you would have to draw in an exam anyway. So how I would draw these is I would start with your carbon-carbon double bond, just as we did with alkanes. Start with your carbon chain. So you can see that I have 2 carbons here, so the double bond is going to have to be between these 2 carbons because they are the only carbons in our chain. So we've represented our double bond by putting 2 dashes in between each of the carbons. That means each of these carbon atoms already has 2 bonds. So for each carbon, we have to think about how many more bonds it needs. And we're going to put hydrogens at the end of these. We know they're going to be hydrogens because this alkenes are hydrocarbons, meaning they contain hydrogen and carbon only. So let's look at the carbon on the left first of all. It already has 2 bonds, so it needs 2 more. Remember, each carbon must have a total of 4 bonds. I'm going to draw them slightly differently than we did with alkanes. If you don't draw these in the right direction or the right angle as such, it doesn't matter in an exam as long as you have the right number of bonds. I'll come back to that in a second, why I've done that. But there's 2 more bonds, and I'm going to put hydrogen at the end. Let's look at the second carbon now. Again, it needs 2 more bonds, and I'm going to draw them out at that angle. The reason why I've drawn them at this angle is because bonds want to be as far apart as possible. Bonds are made up of electrons, they repel each other, and they want to be as far apart as possible. So you can see here I've almost got an angle. You don't need to draw this in. You've got an angle here of 120, 120, 120. So these bonds are as far apart as possible. So again, you don't need to be able to explain that. And even if you don't draw it, that particular angle, it doesn't overly matter. But that would be the general shape of ething. So that's ething. You've got its name, its molecular formula, its structural formula, saying the most important thing there is your double bond with the carbon between the carbon atoms. And ethane would be a colourless gas. As you can see, all of these will be. So let's move on to the next one now. Has 3 carbons. So the next alkene in the series will have 3 carbons. Let's name it first of all. We get the name from the length of the chain first of all. So if there's 3 carbons, that means the start of the name is prop. Because it's an alkene, it ends in ene. Its molecular formula, well, N is 3. And we have twice as many hydrogens as we have carbons according to the general formula. So it's going to be C3H6. But again, you could draw this first and then go back to the molecular formula and write it from your structure. So let's have a think about propane now. So with propane, we have 3 carbons in the chain. We could even draw those first of all, 3 carbons in the chain. But what we know is to make it an alkene, there must be a double bond between 2 of the carbons. It doesn't matter which 2 you do it between, but I'm just going to do it between these 2 here. Okay, so make sure there's a double bond between 2 of your carbon atoms, but there should only be 1 double bond within your whole molecule. So you can see here is our double bond, but the other bond between the 2 carbons should be a single bond, so you should only have 1 double bond within your whole structure. So again, let's think about how many other bonds each carbon needs. So let's look at this first one first of all. It's currently got 2 bonds, so it needs 2 more to make 4. And I'm going to put hydrogens at the end of those bonds. Let's look at our middle carbon. You can see it actually has 3 bonds. So 2 is part of the double bond, but then it's got a single bond in the other direction. So it actually only needs 1 other bond, and we put hydrogen at the end of that. And then finally our carbon at the other end of the chain, it's only got 1 bond at the minute, So it actually needs 3 more. And so we do it as if we were drawing them for an alkane, kind of at northeast, south and west. And we put hydrogens at the end of those. Again, the angles there don't overly matter, but that is as long as you have the correct number of bonds around each carbon atom. And again, it's a colourless gas. So propane's maybe a little bit more tricky to draw, but remember, draw your carbon chain first. Put your double bond in, make sure there's only 1 double bond within your molecule, and then draw your hydrogens around that. Let's move on now to the last 2, and you'll notice how the last 2 actually have the same number of carbon atoms, and that's not an error. You need to know 2 different versions of the alkene that has 4 carbon atoms in it. So we're going to name it in just a second. We're not going to name it right now. But 4 carbons, what you would expect this to be called is 4 carbons refers to bute, and the ending would be ing. So overall these molecules are butene, but you can see that there's 2 versions of them. So we'll come back to their name in just a second. So let's write the formula first of all, and they both fit the general formula. So if the general formula is CnH2n, our formula is going to be C4H8, because 2 times by 4 is 8. So that's going to be the general the molecular formula for each of these molecules. So let's try and draw these molecules. Okay, so let's go with the first one first of all, and we can see we have 4 carbons in the chain. So just as we've done before, let's draw 4 carbons in a chain, just with single bonds. Okay. The reason why we have 2 options with butene is because we have a choice of where to put the double bond. We can put our double bond, the first option is by putting it between the first 2 carbons in the chain, between carbon 1 and carbon 2. So let's do that for this first one. Again, what we want to do then is fill in our hydrogens. So let's look at the very first carbon. It has 2 bonds, so it needs 2 more. And we'll put them out at an angle like this. And we'll put hydrogens at the end. Our second carbon actually has 3 bonds at the minute, 2 to the carbon on the left and 1 to the carbon on the right. So it only needs 1 more. Third carbon in the chain, it currently has 2 bonds, 1 to the left, 1 to the right, and so it needs a further 2 bonds. And we'll put hydrogens at the end of that. And then our final carbon in the chain, carbon number 4, has 1 bond at the minute, so it needs 3 more to make a total of 4 bonds. And we put a hydrogen at the end of each of those. So there's our structural formula, and again, it's a colourless gas, as all of these first few alkenes are. To name it, we need to think about where we've put the double bond. And to do that, we need to number our carbons. And the rule with naming organic molecules is that the carbon chain is always numbered from the lowest carbon. The functional group must always be on the lowest carbon. So let me show you what I mean. Essentially, we could number this 2 ways. Don't write this in for now. We could number this 1, 2, 3, 4. Or we could also number it the other way. 1, 2, 3, 4. We could number it from right to left rather than left to right. But one of these ways is correct and one of these ways is incorrect. And numbering it right to left in this case is incorrect. And that's because you can see the functional group is here. And as I said, the rule in naming organic molecules is that the functional group must be on the lowest number carbon. So if we've put it from right to left, we can see that the functional group here, our C carbon-carbon double bond, is between carbon 3 and carbon 4. That breaks the rules because what we want is the functional group on the lowest number of carbon. So actually this, numbering it from left to right, is the correct way to number it, because we can see our double bond in this case is between carbon 1 and carbon 2. And we actually incorporate that into the name, and it comes in between the start of the name and the end of the name. So our name still starts with but, B-U-T. But instead of going straight to the ending, I actually put a little dash in. And after the dash, I put a number in. And that's the number that represents where the double bond is. The double bond we can see in this example is between carbon 1 and carbon 2. So we call this but 1. Then we put a dash. And then we end it, as before, with ing. But 1 ing. Why have I called it but 1 ing and not but 2 ing? Well, we always go with the lower number of carbon. So if it's between carbon 1 and carbon 2, then we call it but 1 ing. So you always pick the lower number. So that might seem a bit confusing for now, but let's look at the next example and see if we can see the link with that one as well. So we can see here we're just working on another butene in this case, but it'll be a slightly different structure of butene. You can see it's got the same molecular formula, it's got the same total number of carbons and hydrogens. But let's look at its structure. So again, let's draw the carbon chain first of all. So 1, 2, 3, 4. So our next option with butene is putting the double bonds between the second and the third carbon. So if I put it in the middle, this is now between the second and the third carbon. We'll come back to that in a second, but let's fill in our hydrogens. So we can see our first carbon has just one bond, so it needs 3 more. 1, 2, 3. And we put hydrogens at the end of each of those. Our second carbon, you can see it has 3 bonds currently, 1 to the left, 2 to the right. And so it needs just 1 more bond, and we put a hydrogen at the end of that. The third carbon in the chain also has 3 bonds presently, 2 to the left and 1 to the right. And so we need just 1 more. And then our final carbon in the chain just has 1 bond at the minute, so it needs 3 more, and we put hydrogens at the end of each of those. So you can see if we wanted to count up our hydrogens in total, we have 3 in the first carbon, and then plus 1 more in the next one is 4, plus 1 on the next one is 5, and then 3 more on the end one, which is 8. So it follows the formula that it should have, C4H8. So you can see we have a slightly different structure here because the double bond is now in the middle. So let's number our carbons, remembering we want the functional group to be between the lowest number of carbon. So if we number it left to right, 1, 2, 3, 4. Okay, and let's number it now right to left, 1, 2, 3, 4. In this case, you can see it actually doesn't matter which way we number it, because if we look at the double bond, either way we number it, the double bond is between carbon 2 and carbon 3. So actually it doesn't matter whether we number this one left to right or right to left, but we see it did matter in the previous example. So let's try and name it now. So again, the start of the name is always determined by the length of the chain. Because we've got 4 carbons in the chain, the start of the name is but. Then we put a dash, and then we want to put the number of our functional group. So as we said, the functional group is between carbon 2 and carbon 3. So which number do I write down? Do I write down 2 or do I write down 3? I write down 2 because remember we always go with the lower number. So this is but 2 dash ing. So we would represent that name by but dash 2 dash ing. When we're saying it out loud, when we're naming it, we would just call it but 2 ing. So you can see here we've got 2 molecules that have the same molecular formula. So you can see but 1 ing has a molecular formula of C4H8 and but 2 ing has a molecular formula of C4H8, but their structural formula is different in that in but 1 ing the double bond is between carbon 1 and carbon 2, and so we call it but 1 ing, and in but 2 ing the double bond is between carbon 2 and carbon 3, and so we call it but 2 ing. Now, you might be thinking that there is a third possibility. Why don't we put the double bond between carbon 3 and carbon 4? Well, let's draw that really quickly and show you why that doesn't actually work. So if we draw 4 carbons in the chain, first of all, and what we're saying is that we should put, a third option could be to put the double bond between carbon 3 and carbon 4. Let's throw in our hydrogens just to make this complete. So our end carbon will need 3 more bonds. Our second carbon will need 2 more bonds. Our third carbon only needs 1 more bond. And our final carbon needs 2 more bonds. So let's now try and name this. So if we number it from left to right, we go 1, 2, 3, 4. And in this case, our double bond is between carbon 3 and carbon 4. And so we would call this but3ene if we numbered it from left to right. But is that correct? No, it's not. Because our other option is to number it from right to left. 1, 2, 3, 4. In this case, our double bond is between carbon 1 and carbon 2. And what's the rule? The functional group should always be on the lowest number of carbon. In this case, it would be called but1ene because it is between carbon 1 and carbon 2. And this is the correct name because we have numbered it in such a way that the functional group is on the lowest number of carbon. But3ene actually doesn't exist. It is essentially just but1ene. Essentially, we've got but1ene, and that's exactly what we drew in our table for but1ene. It's just drawn the other way round. So you can see that I can technically just flip this round. I know my carbons are back to front, but look, that's exactly what we drew for but1ene. So essentially, but3ene is the exact same thing as but1ene. We've just rotated it around, but you would never call it but3ene. Its proper name would be but1ene. So you can see there from butene onward, so for longer alkenes, there's going to be a choice of where you put the double bond, and actually that will affect the name of it. So you could in an exam be asked to draw specifically but1ene or but2ene, or you could be asked to draw one of these. You could be asked to draw butene and then name it, give it its specific name. And wherever you put the double bond, that's going to determine the name of it. So just be really careful with that. So just down below that table, you just have a couple of notes on why methane doesn't exist, and notes on the 2 butene structures, how they have the same molecular formula but a different structural formula. So the key thing here is that you're confident in being able to draw your first 4 alkenes, so for ething, propane, and the 2 different forms of butane, and be able to draw them, remember their molecular formula, or be able to work out their molecular formula from their structural formula, and remember that they are all colourless gases. So that's quite easy to remember, because they are all colourless gases. So a couple of ways even from this table that we can see that these molecules fit the definition of a homologous series is firstly that they have the same functional group. They all have a carbon-carbon double bond within their structure. They follow the same general formula, CnH2n. We've written that at the top of our molecular formula. And also the formula of our consecutive alkenes differs by a CH2 group. Remember, that's the end of our definition of a homologous series. So if we go from ethene to propane, well, what are we adding on? So to go from ethene to propane, we're adding on 1 carbon and how many hydrogens? 2. To go from propane to butane, we're adding on 1 carbon and 2 hydrogens. It doesn't work going from but1ene to but2ene because I'm not adding on an extra carbon, and those are just different forms of the same molecule, different forms of butane. But going from ethene to propane and from propane to butane, you can see that we're adding on a CH2 group. So it fits this definition of a homologous series in that way too. And the top of page 5 just goes over that as well. You can see from the table that they follow the same general formula. The formula of 2 consecutive alkanes differs by a CH2 group. And alkanes will also have similar chemical properties, and that's because they have the same functional group. If you remember, I talked about the functional group is where the chemistry happens, where the reactions will happen. So that's why they have similar chemical properties. They'll react in the same way because they have the same functional group, and that's where the chemistry, that's where the reactions happen. And they show a gradation in their physical properties, and what that means is we'll see a slight change, a slight progression in their physical properties. So for example, those first few alkenes that we looked at were all colourless gases, but eventually as the chain gets longer, the boiling point will increase, in which case they will start to become liquids at room temperature. And in one of these reactions, you'll see me doing this reaction in the lab, and you'll see that the alkene I use is a liquid. So alkenes can be liquids, and that's because the longer their chain is, the higher their boiling point is, which will make them liquids at room temperature. So you could write in something like that on that point, that the boiling point will increase as the chain gets longer. So what we're going to do now is we're going to look at the reaction of alkenes. And as we've already said a few times, alkenes are more reactive than alkanes because they have this carbon-carbon double bond functional group. So let's maybe write that off to the side. So alkenes are more reactive than alkenes because of this functional group. So we'll see that alkenes essentially do more than alkenes. The first reaction we're going to look at is combustion, and we'll see how combustion happens exactly the same way as alkenes. With alkenes, combustion was their only reaction because they're fairly unreactive molecules, but with alkenes, this is just one of its reactions. So again, alkenes can be used as a fuel. When we burn them, they release a lot of heat, they release a lot of energy that can be used as a fuel. And we'll see that this is exactly the same type of reaction as alkenes. So as with alkenes, we have an option essentially. Either they will undergo complete combustion if there is an excess of oxygen, and in that case our products will be carbon dioxide and water, just as it was with alkenes. But if there's a limited supply of oxygen, they will undergo incomplete combustion. That's if there's a limited supply of oxygen, and our products, rather than being carbon dioxide, will be carbon monoxide and water. So let's summarise these in the boxes below. So if we have an excess supply of oxygen, our alkene will burn in that oxygen, the excess supply of oxygen, to produce carbon dioxide and water. It will burn fully, producing carbon dioxide plus water. But if we have a limited supply of oxygen, our alkene will react with that oxygen to produce carbon monoxide and water. So it doesn't burn completely. We call this incomplete combustion. So it's really important in an exam that you're watching carefully whether they say this is a reaction with excess oxygen or with a limited supply of oxygen. If it is excess oxygen, your products will be carbon dioxide and water. If it's limited supply of oxygen, your products will be carbon monoxide plus water. Now, in the case of alkenes, you don't need to be able to write the balance symbol equation, but they could ask you what the products are, so it's important that you know this. The last thing to mention with alkenes and their combustion reaction is that they burn with a more luminous, and that just means a brighter orange and more smoky or sooty flame than alkanes, and that's due to their higher ratio of carbon to hydrogen atoms in an alkene, essentially because there are less hydrogens per carbon atom. If you remember our general formulas for alkanes, the general formula is CnH2n plus 2. For an alkene, the general formula is CnH2n. And so you can see for alkanes there's more hydrogens per carbon atom. For alkenes there's less hydrogens per carbon atom. And how we can also refer to that is by saying alkenes have a higher ratio of carbon to hydrogen in the alkenes. And that actually causes this more luminous, this brighter orange and more smoky flame. Sometimes that can be written as a sooty flame. So essentially if we were to burn an alkane and to burn an alkene beside each other, you would see more smoke coming up off an alkene. You would see a brighter, more orange flame with an alkene than with an alkane. So they could ask you that in an exam. How would an alkane burn compared to an alkane? So alkane would be like a cleaner flame. Alkenes burn with a more luminous, in other words brighter, orange and more smoky or sooty flame than alkane. So make sure you learn that. That's an important observation, and because you don't have to be able to write balance symbol equations for the combustion reactions in alkenes, it could be something that they do pick up on and say, what would you observe when you're burning an alkane? And you would say a luminous or bright orange and sooty flame. So the next reaction we're going to look at is called addition polymerization, and that sounds much more complicated than it is. Essentially all that happens is that single alkene units join together to form a long chain. And that's simply it. Why can they do this? Well, they can do this again because of that functional group, because of the carbon-carbon double bond. So let's fill in your notes here. It says polymers are produced by the addition polymerization of alkenes. In these reactions, monomers, which are our single alkene units, react together to give polymers, which are our long chains of alkenes essentially. So it says here monomers are small molecules that can bond together to form a long chain. A polymer is then a long chain molecule formed from the large number of monomers bonded together. So essentially monomers are your single units that are joining together to give you a long chain. And polymerization is the process essentially. Polymerization is the joining together of small molecules, monomers, to form a large molecule. And that word monomer literally means one molecule. So remember when we are naming things like carbon monoxide, monoxide means one oxygen. So mono means one. We talked about, think of a monobrow as essentially one eyebrow. Monomer means one and mer means molecule. So monomer means one molecule. Polymer then, well, poly means many, and again mer means molecule. So polymer means many molecules. So monomer is one molecule, polymer is literally many molecules. The way I like to think of this reaction is like making a people paper chain. You might have done this when you were younger. So you have this little man that you've cut out, you've folded a piece of paper together, and what you actually cut out is one little man. But then when you open out the chain, what do you get? You get a long chain of these little men. You open it out and you see this long chain of people. So in terms of our polymerization reaction, this one man would represent a monomer, this one molecule, and the long chain would represent our polymer. So the polymer is made up of many small units, the same units. So take one monomer and add them and add them and add them in the chain together, and you get this polymer. So let's look at an example of a polymerization reaction with an actual example of an alkene. We'll take, for example, ething. This is one specific reaction that you need to be aware of, but you don't need to be able to write an equation for this as such, but you do need to be familiar with the reaction. You could be asked to describe the process. You could be asked to draw a chain to represent the polymer. You could be asked to recall that the process is called addition polymerization. But this hopefully will also help you understand the process. So what I'm going to do is I'm going to draw 3 ethene monomers. I'm going to draw them in different colours. So let's think about what ethene is. First of all, the eth part tells me that I have 2 carbons. And the ene part obviously tells me that this is an alkene. So we've got 2 carbons in the chain, so let's draw that first of all. And we know that alkenes must have a double bond, so we'll put a double bond between those 2 carbon atoms. Let's fill in our other bonds, and they will have hydrogen at the end of them. So let's look at the first carbon. It has 2 bonds, so it will need 2 more. And we put hydrogen at the end. And the second carbon has 2 bonds, so it will need 2 more. So there's one ethene molecule, and we refer to that as a monomer. And what I'd like you to do is I'd like you to draw 2 more of those, but in different colours. So this is one ethene monomer. I'd like you to draw 2 more. So each of these 3 individual ethene molecules are what we refer to as monomers. They are single units, they're single small molecules. So what actually happens during this polymerization reaction? Well, the first thing that happens is that the double bond between the 2 carbon atoms, it breaks. So the double bond breaks. And so what we're left with is a single bond between our carbon atoms rather than a double bond. So let's draw that for our first monomer. So rather than having a double bond, I have a single bond between my 2 carbon atoms. But what has happened to that double bond? Well, essentially it has broken. The second of the double bond breaks, and you can think of it as almost half going this way and half going that way. So you'll see I've done that bond slightly shorter. So it's half the bond is on one side of the first carbon and half the bond is on the other side of the second carbon. And what that's representing is essentially 1 electron on either side of those carbons that is ready to form a covalent bond with another electron essentially. So it's ready to pair up with another electron and form a bond. So essentially what that short little line is representing on either side of the carbon atoms is that you've almost got half a bond there that is ready to join up with another half bond and form a full bond, and that will start adding towards towards the chain. So let's draw that for each of our monomers. So you can see the same thing has happened for each monomer. The double bond is broken. We now have a single bond between our carbon atoms, and there's almost half a bond on either side. What happens now is that these individual units, they join up and form a long chain. So remember I said there was almost half a bond at either side of the carbon atom ready to form a bond with another half bond. And well, that's essentially what happens here. So if you can imagine this half bond here joining up with this half bond to make a full bond. So what we've drawn here is our first 2 units joined together now by a full bond. So our second purple carbon has formed a bond with the first blue carbon as such. But you can see in our blue monomer unit that it's got a half bond on the end of it. It's ready to form a bond with another half bond. And what it does, the half bond, which was essentially here in the monomer unit, forms a bond with this half bond here of our green monomer unit. So let's draw that in. So it will then form a bond with the green monomer unit. But that also has a little half bond which is ready to form a bond with another monomer unit. So if we had another monomer unit, we could add it in here. And this process goes on and on and on and repeats and repeats and repeats hundreds or even thousands of times to form these really long chain polymers, which have really important uses like in plastic bags and other plastics that we use in our everyday life. So looking at the whole process overall, we started on the left-hand side with our ething monomers. So our ething monomers on the left-hand side. And what we formed at the end is this long chain is called polyething. So literally many ethings. Sometimes that's abbreviated down to polythene, which you may be familiar is probably one of the most common plastics. It's used in packaging, it's used in plastic bottles and so on. So this chemical reaction is actually a really, really important industrial process that allows us to form materials that we use in our everyday lives. So this overall representation is showing us the polymerization of ething, starting from our ething monomers and finishing with our polyethene or polythene polymer. So if you wanted to write on the right hand side that this is our polymer. We started with many monomers, many individual units, and they have essentially joined together to form a long chain, which we call a polymer, literally many molecules joined together. Why does that happen? It happens because the double bond breaks, opens up and allows more bonds to be formed. So let's look at another example. This is the second example you need to be familiar with, and this is of chloroethane. Chloro, what do you think that means? Chloro literally means that there's a chlorine atom on the ethene molecule. So let me draw chloroethane for you. So if we draw our normal ethene molecule, except I'm not going to draw all my hydrogens in just at present, because what we're going to do this time is we're going to swap one of our hydrogen atoms for a chlorine atom. So instead of being C2H4, actually one of those hydrogens is replaced with a chlorine atom. But the rest of the atoms at the end of these bonds are going to be hydrogen atoms. So this is chloroethane. And this represents our monomer in this reaction because it's our single unit, our starting molecule as such. So just as before, what's going to happen is this double bond is going to open up and form a half bond on either side of those two carbon atoms. So let's show that first of all. So our double bond now becomes a single bond because one of those bonds has broken. And don't forget to draw your little chlorine atom instead of your fourth hydrogen. So what we've got now is a single bond between our two carbon atoms and a little half bond either side. And remember, those half bonds either side are showing that it's ready and available to link up with another half bond to add on towards the chain. So let's imagine we had another monomer. That would just bond on here. And again, at the other side, we would have a little half bond that was ready to form a bond with another half bond and just add another unit onto the chain. And this process goes on and on and on. And what you can see is you're just adding more and more of the same unit each side. And you know, it could add on this side as well. But what these little half bonds at either side is showing is that this process can keep going on. This can continue on and on and on. So what have we got within this molecule? We'll look at this a little bit more closely than we did with polythene. What we've got is our what we call a repeating unit. So this is our repeating unit because you can see that is the same as the next little repeating unit. If I maybe go over that in purple. Those two inside the blue bracket and inside the purple bracket are exactly the same. Those are what we call our repeating units. So if you maybe want to add that to your diagram, these are what we call repeating units. So that's essentially what repeats multiple times within the chain. So actually we can abbreviate this, this long chain into a simpler diagram. And essentially how we do that is we draw one repeating unit. So if you draw one repeating unit, and then just as we have done, draw square brackets around that. But what's really important is that you make sure that these bonds either side of the carbon atoms actually go through the bracket, because what that shows is that this will continue to repeat. There will continue to be units added on to this one either side. And how we represent that multiplies and that adds on multiple times is that we put a little n in the bottom right hand corner outside the square brackets. So essentially this unit repeats n times, and that then represents our polymer. So that's a general representation for the polymer. So we put our repeating unit inside, put square brackets around it, and put an n in the bottom right hand corner to represent that this repeats n times. So you might want to add that to your diagram. This unit repeats n times. But in order for that to repeat n times, I would need n of my starting monomer. So how we represent that is almost like a balanced symbol equation, where you put numbers in front of the formula to represent how many of that molecule you need. We're going to do that in this diagram as well by putting an n in front of my monomer. And that just shows that n monomers the double bond will break and they'll join together to form a long chain that will repeat n times, because as many monomers as you have will add on to the polymer. So you need the same amount of monomers as how many repeats there are in your chain. And if we were to do this for ething, just for a little bit of practice, if we have a look at what the repeating unit is in ething, I'll maybe zoom in on this. So our repeating unit this time is essentially what was our monomer, which was ething, but without our double bond. So this is our repeating unit for polyethylene. So how we could represent that would be like this. So our repeating unit is essentially an ethene molecule, but with a single bond instead of a double bond. And then we want to draw that bond extending out through our square brackets to show that would repeat n times. Okay, so this is equivalent to this abbreviated diagram of the long chain, which just shows your repeating unit multiplied n times. Let's briefly just go back to our polymer of chloroethene for a second, just to name that. So if you could write this underneath, that the polymer of chloroethene is simply polychloroethene. But do remember that our double bond is now broken, so never put a double bond in your polymer diagram. The double bond has broken, so really there's no alkene molecules anymore because there's no double bond. But we still call it polychloroethene. We literally just put poly in front of the name of the monomer. The initial monomer was chloroethene, and we just shoved the word poly in front of it. Now, sometimes this is called polyvinyl chloride. Okay, and you may think, why are you telling me this? But the reason is because if we take P, V and C, you may have heard of PVC, which is another commonly used plastic, such as in building and construction, and sometimes even in pipes. So you may have heard of PVC, and that's actually what this molecule is. This molecule is PVC. So for this polymerization reaction, basically what you need to be able to do is to describe this process, describe how polyethylene can be formed from the ethene monomers, and how polychloroethene can be formed from chloroethene monomers. Describe that process and make sure you know what monomers are and what polymers are. And lastly, in this section, we're going to look at the reaction of alkenes with bromine. And this is a really important reaction because it can be used to test between alkanes and alkenes, because quite often alkanes and alkenes will look the same. You'll have seen from our study of them that they're often colourless gases or even just colourless liquids, so it can be very hard to tell between them. So this can be used as a test to distinguish between alkanes and alkenes. So essentially what we do, just like if you were describing how you test for carbon dioxide, first of all you describe what you do, second of all you describe what you see happening if that particular gas is, say for example, carbon dioxide. Your test would be bubble the gas through lime water, and your result would be the lime water changes from colourless to milky. So it's a bit like this if you were asked to describe the test for bromine, and make sure you know this really well. So essentially what you do is you add the test substance. That's essentially what you're trying to test if you're testing an alkane or an alkene, for example. So add the test substance to bromine water and mix well. If a carbon-carbon double bond is present, a colour change from red-brown to colourless will occur. Now, red-brown is the colourless of pure bromine, but if you're using bromine water, it's more of an orange colour. So I'm actually going to get you to change that in your notes. Red-brown, again, is the colour of pure bromine, but if we've made an aqueous solution of it, it'll be more of an orange colour. So if you could change that to orange, that's the one they more look for in the exam. So if a carbon-carbon double bond is present, a colour change from orange to colourless will occur. If the test substance is saturated, what do we mean by that? Well, we described alkanes as saturated. So alkanes are saturated, and they will not possess carbon-carbon double bonds. Okay, so if the test substance is saturated, for example alkanes which have no carbon-carbon double bonds, the solution will remain, and again I'd like you to change that to orange. So essentially if it's an alkene, it will turn bromine water from orange to colourless. If it's an alkene, it will remain orange. I've got a video of me carrying out this reaction which we'll look at shortly, but very briefly let's just see why this happens, and we'll see the colour change with ethene with this one as well. Okay, so first of all what I'd like you to do is draw ethane. You should be able to draw that yourself now. So ethane, the eth part of it means how many carbons is there? There's 2 carbons. Okay, and this is ethane, so it's an alkane. And you might want to write that at the side, that this is your example of an alkene with bromine water. So let's draw ethane. Remember, alkanes have single bonds between the carbon atoms, and so let's think how many other bonds we'll need. This carbon will need 3 other bonds, and this carbon will need 3 other bonds, and we'll put hydrogen at the end of those. Okay, if we were to add bromine into this, now bromine is Br2, remember it is diatomic. Well, what you can see from your ethane molecule is that there is no space for our bromine to add on. There's no space for our bromine atoms to add into our ethane because the molecule is already saturated. There's already 4 single bonds around each of my carbon atoms, so it doesn't have any room for any more. So actually, no reaction happens. So no reaction. And that's because ethane is saturated. So no reaction happens, and if we've mixed these two together, well, ethane is colourless, but bromine water is orange. So if no reaction takes place, then the solution remains orange because no reaction has taken place. So the bromine water will remain orange. So the solution remains orange. But let's have a look at what happens if we react it with ethene. So again, eth is 2 carbons, and this is our example of an alkene reacting with bromine water if you want to add that in. So with ethene we have 2 carbons in our chain, but this time we have a carbon-carbon double bond rather than a single bond. Let's think how many other bonds we need. Well, this carbon needs 2 more bonds, this carbon needs 2 more bonds. And let's draw our hydrogens at the end of those. So this is ethene. It's an alkene. And if we add bromine to it, which again remember is orange, bromine water, what will happen this time? Well, this time what can happen, a bit like with our addition polymerization, is that that double bond can break and essentially it can form an extra bond on each of the carbons. So let's have a look at that. So if you draw your arrow in, so the first thing that happens is that the double bond breaks. And then what happens is the bromine can add across the double bond essentially. So let's see that in action. So our double bond breaks. And let's draw our 4 original hydrogens on. So our double bond has broken and you can see each carbon now only has 3 bonds around it. So we need an extra bond which we'll draw down here. And what happens is that your 2 bromine atoms, they add across the double bond. What we mean by that is essentially that one bromine atom adds to one carbon and the other bromine atom adds to the other one, because you can see we've got Br2, which is 2 bromine atoms covalently bonded together. So one bromine adds to one carbon atom, the other bromine adds to the other one. Okay, this molecule here, it's actually called 1,2-dibromoethane, but you don't need to know that. But what you do need to know is that this molecule is colourless. This molecule is colourless, and that explains the colour change from orange to colourless. So because bromine water is adding to this ethene molecule to form a new molecule, it has now lost its orange colour and become colourless. Okay, so you might want to write a little summary at the bottom. That if you mix an alkane and bromine water, the solution remains orange. But if you mix an alkene and bromine water, the solution changes from orange to colourless. So you need to learn your procedure, learn the test, that you mix, make sure you mix them well. If an alkane is present, the solution will remain orange, but if an alkene is present, the solution will change from orange to colourless. And you could be asked that in maybe a 3 or 4 mark question. How would you distinguish between the likes of hexane and hexene? And you would have to describe what you do and from your results state how you would tell which was hexane and which was hexene. So hexane would be the one that remains orange when mixed with bromine water, but hexene would be the one that changes bromine water from orange to colourless. And the next little video is going to show you how you carry this out in the lab and just actually shows you this in action. So the reaction we're going to do here is the test for alkenes. So as we've already talked through, the test for alkenes is using bromine water. So what I'm going to do is just put a really small amount of bromine water in each of these boiling tubes. You can see that bromine water is a strong orange colour. Okay. So there's bromine water, and that's in our 2 boiling tubes. And what I'm going to do is I'm going to add an alkane to one of my boiling tubes and an alkene to the other. So here is my alkane, and it's called hexane. You don't need to know that one. But it's called hexane. Ends in A-N-E, so we know it's an alkene. If I shake bromine water with it, what you can see is that the bromine water just stays orange. Okay, so we know that it's not an alkene. Alright, What I'm going to do now is to my other boiling tube, I'm going to add an alkene. It's called cyclohexene, ends in ENE. So we know that it is an alkene. Okay, what I'm going to do now is stopper it and shake it. And what you can see is that it has decolorized my bromine water. Okay, so the orange colour of my bromine water has disappeared, and instead of an orange solution we now have a colourless solution. You can see the different layers, and that's just because cyclohexene is not completely soluble in an aqueous solution, so don't worry about that. But what you can see is that it has decolorized your bromine water. So we can see that this one is an alkene because it has turned bromine water from orange to colourless, and this one is an alkene. It's already saturated, it can't form any bonds with the bromine water, so it has stayed orange. So that's us finished with alkenes. So just a quick run through of what you need to know with alkenes. Make sure you know that their general formula is CnH2n, that they have a functional group which is a carbon-carbon double bond, and that makes alkenes more reactive than alkanes because that's where the chemistry happens. You need to be able to draw the structures of ethene. Remember, there's no methane because we have to have at least 2 carbons. You must be able to draw it for propane, but1ene and but2ene. So make sure you can draw those structures confidently. And then you need to be able to recall reactions of alkenes and describe these. So first of all, we looked at combustion, and with that you must have learnt your products for incomplete combustion being carbon monoxide and water, and for complete combustion being carbon dioxide and water. We then looked at addition polymerization. Make sure within that you know the definition of a monomer, of a polymer, and to be able to describe the process of the addition polymerization. And then finally we looked at the reaction with bromine water, and that can be used as the test between alkanes and alkenes. So that finishes off our alkene section of this topic, and the last section of this topic in the next video we'll look at alcohols and carboxylic acids.